Alright guys, so in this video we're going to talk about the Graeco Latin square design. So this is very similar to the Latin square design, but in some experiments we may need to block in three directions, and to do this we introduce the Graeco Latin square design. So we're just going to jump right into an example. A research institution is interested in determining the effect of 5 different methods when determining the mean amount of mercury in a solution. To determine the mean amount of mercury in grams, a population of 5 chemists at the research institution test 5 batches of solution with 5 different pipettes. So importantly, we have 3 different blocking variables. So we have 5 different chemists, 5 batches of solution, and 5 different pipettes. So how do we go about analyzing this? So here's the design of the experiment. Basically, we have, as mentioned beforehand, we have 5 methods labeled A through E, all capital Latin letters, and then we have 5 chemists labeled A through E, lowercase Latin letters. Typically, you would use Greek letters like alpha, beta, gamma, and so on and so forth, but we've just used lowercase Latin letters for simplicity. But that is where the name Graeco Latin square comes from, is you would typically use Latin or Greek letters for one of the blocking effects. So then we have our 5 pipettes labeled 1 through 5, and we have our 5 standardized solutions or 5 batches labeled 1 through 5. So for the first batch, each chemist would measure the amount of mercury by a randomly assigned method labeled A through E and pipette, so that each method and pipette are used exactly one time. So when we repeat this process, we repeat it for the rows, and the result is a Graeco-Latin square. So here's what the data looks like from the experiment. We have our data here. Now I do want to point out a couple important things here, but each uppercase letter, so each method appears only once in each row and column. So you can see A here in each row, or in this row and in this column. It's the only A. You can look at it in this one too. It's the only A there, so on and so forth, and you can check that for all of the uppercase letters, so the methods in this case. And in addition to that, so what would typically be the Greek letters in our case is the lowercase Latin letters, which represents the chemists. Those also appear exactly one time in each row and column. So you can see this this lowercase a is the only A in this row and in this column. And you can go through and check it for all of them. And then in addition to that requirement, each pair of lower and uppercase letters appears exactly once in the entire square. So E happens with B only one time. So you can't find E and B anywhere else paired together like that throughout the rest of the Graeco-Latin square. So the net result is that each chemist uses each method only one time and analyzes each batch only one time and uses each pipette only one time. So that's basically how the Graeco-Latin square is constructed and how we block 3 variables. So the model for a Graeco-Latin square experiment is extremely similar to a regular Latin square experiment. The only difference is you have one extra term to describe the third blocking variable. So YIJKL is the observation in the ith row and jth column receiving the kth Latin treatment and the lth Greek treatment. So just to clear up confusion, this would be our lower case Latin letters here in our case. Typically, they would use Greek letters. Mu is the overall mean. Tau I is the effect of the ith method on the amount of mercury. Beta J is the effect of the jth chemist on the amount of mercury. Alpha K is the effect of the kth pipette on the amount of mercury. And gamma L is the effect of the lth batch on the amount of mercury. So, and then finally, epsilon IJKL is the random error, which we assume follows a normal distribution with a mean of 0 and an unknown standard deviation of sigma. Also, like the Latin square design, we assume that the standard deviation sigma is the same among all treatments, so methods in this case, all blocks, and all blocks, which is pipettes, batches, and chemists in this case. So fitting the statistical model to the data is very easy with our best friend Minitab here. Basically, you just have one extra column for the Greek treatments or lowercase Latin letter treatments here, which we can see is the chemist in this case. So you're going to go in, punch in all the data, and then you're going to go into the typical ANOVA. So you go stat, ANOVA, general linear model, fit general linear model. And then you're going to choose the responses, which in this case is the amount of mercury, and then your factors, which is batches, pipettes, chemists, and methods. And then you're going to hit go. You get your output from Minitab, and here it is with some of the highlighted effects here. So we can see that the effects of the different chemists is significant at a 10% significance level. The effects of pipettes are significant at a 5% significance level, and the batches are significant at a 5% significance level as well. So I'm just going to read this off for one of these. Those are the blocking effects. So since the p-value for the pipette and batch blocking effects are both smaller than 0.05, at the 5% significance level, the sample data provides sufficient evidence to conclude that the blocking effects of pipettes and batches are statistically significant. And then you can, go on and read it for the other one there, but I'm not going to go through that. I'll leave that up to you guys. So then next, after we've established which blocking effects are significant, we look at the p-value for the treatment effect, so the methods in this case, and we see that it is also significant at a 5% significance level. So then we go through the interpretation. So since the p-value for the method is smaller than 0.05, at the 5% significance level, the sample data provides sufficient evidence to conclude that the treatment effect of the method is statistically significant. So in other words, the mean amount of mercury found is significantly different among the 5 different methods. So last but not least, we're going to check the assumptions of the statistical model. So basically, we want to check whether we assume that the random error follows a normal distribution with a mean of 0 and has an unknown standard deviation of sigma. And additionally, we also assume that the standard deviation of sigma is the same among all of the treatments and all of the blocks. So to test these assumptions, we use the same as we've always used throughout this course, but basically we're going to use the residuals. And so first we're going to start off with checking the equal standard deviation assumption. So we can perform Levene's test for equal variance to test whether the standard deviations are statistically different. So we go using the residuals, we go stat, ANOVA, test for equal variances. And then we get our Levene's test results, which, as we can see here, for the method and chemists are both statistically insignificant. In other words, the p-value is greater than 0.05, as well as for the pipettes and batches, they're also not significant. So since none of the p-values are less than 0.05 at the 5% significance level, we do not have sufficient evidence to conclude that the equal variances assumption is not valid, and therefore we do not reject the equal standard deviation assumption. So then lastly, we're going to check the normality assumption. So we're going to use the residuals to make a histogram and normal probability plot. And so as we can see here, I mean, it's close to not being normal, but the p-value actually does show here that it is approximately normally distributed. So we do not reject the assumption that the random error follows a normal distribution, and therefore the conclusions drawn from the ANOVA test are valid. So guys, that's basically it for the Graeco Latin square design, and basically the only difference that the key things to remember is that each of the uppercase Latin letters appears exactly one time in each row and column. Same with the lowercase letters, and then each pair of the uppercase Latin letter and lowercase Latin letter appears exactly once in the entire Graeco Latin square. Other than that, it's a very similar analysis to a regular Latin square. The only difference here is that we've got a third blocking variable. All right, guys, so thanks for watching. I hope this was informative. And again, you can practice the questions, practice the question that we've worked out here, as well as as an extra question that we've included at the end of the slides. Okay, guys, so thank you very much, and that's it. All right.